Welcome to the Advanced Building Materials Sustainability Professional course, a comprehensive program designed to equip you with the knowledge to reduce carbon footprints and enhance the sustainability of our built environment. This course is essential for architects, engineers, and professionals committed to sustainable building practices. The built environment is a major contributor to global carbon emissions, with operational and embodied carbon playing significant roles. Understanding these contributions is crucial for effective carbon reduction strategies. As we aim to reduce operational carbon, embodied carbon is becoming a larger share of total emissions. This shift highlights the need for targeted interventions in building materials. Embodied carbon is a critical focus due to its temporal irreversibility, making it a priority for carbon reduction efforts. Addressing it now can prevent long-term environmental impacts. Different building types have varying levels of embodied carbon, emphasizing the need for tailored carbon reduction strategies across the construction industry. The global construction industry is vast, with significant material use and spending. This scale underscores the importance of sustainable practices to reduce carbon footprints. Cement and steel dominate building material production by volume, presenting key opportunities for carbon reduction strategies due to their high carbon intensity. Understanding the carbon intensity of different materials is essential for developing effective sustainability strategies in construction. The embodied carbon intensity of materials varies greatly, offering substantial opportunities for designers to make impactful substitutions. Regulatory and market drivers are increasingly pushing for sustainable building materials, transforming sustainability from an option to a necessity in construction markets. A global regulatory timeline shows the increasing mandates for embodied carbon reporting, highlighting the growing importance of sustainability in construction. Key sustainability frameworks and standards guide the building materials industry, ensuring comprehensive and effective sustainability practices. The sustainability hierarchy prioritizes actions to minimize environmental impact, guiding decision-making in material selection and usage. This course is designed for professionals across various roles in the building industry, focusing on sustainability in materials and construction practices. Building materials sustainability presents significant economic opportunities, including market growth and premium valuations, while also addressing key risks. The green building materials market is experiencing rapid growth, driven by increasing demand for sustainable products and practices. Throughout this course, you'll gain expertise in life cycle assessment, carbon quantification, material categories, and more, preparing you for leadership in sustainability. The Edge Amsterdam case study highlights successful sustainability practices, demonstrating the tangible benefits of advanced building materials strategies. The central challenge of net zero construction is addressed through comprehensive training in analytical tools, material knowledge, regulatory insight, and professional impact. Every building material has a story that begins long before it arrives on a construction site and continues long after the building it becomes part of is eventually demolished. Life cycle assessment, or LCA, is the internationally standardized scientific methodology that makes these invisible impacts visible. In this CDG training chapter, you will develop a comprehensive and technically rigorous understanding of LCA, how it is structured, how it is conducted, and why understanding it is applied in building materials sustainability practice. A ton of structural steel begins its life as iron ore extracted from a mine in Brazil or Australia, travels to a blast furnace where it is smelted at temperatures exceeding 1,500 degrees Celsius, is rolled into structural sections, transported by ship, rail, and road, cut, welded, and galvanized, delivered to site, erected, bolted, and fireproofed, and eventually, decades later, dismantled and either recycled or sent to landfill. The history of life cycle assessment dates back to 1969 with the Coca-Cola bottle study by Midwest Research Institute. Over the decades, the methodology evolved from energy accounting to broader environmental analysis, with significant milestones in the 1970s and 1980s. The formation of SETAC in 1979 and the publication of ISO standards in the late 1990s and early 2000s solidified LCA's role in environmental assessment. ISO 14040 structures the LCA process into 4 interconnected phases that together constitute a complete and credible environmental assessment. The iterative nature of LCA, with interpretation feeding back into earlier phases, reflects the need for continuous refinement as data quality and methodological approaches improve. The 4 phases of the ISO 14040 LCA framework include goal and scope definition, lifecycle inventory analysis, lifecycle impact assessment, and interpretation. Each phase plays a crucial role in evaluating the environmental impacts of a product throughout its lifecycle, from raw material extraction to end-of-life processing. The N15978 framework is the most widely used for defining LCA system boundaries in the built environment. It divides the building lifecycle into a series of numbered information modules, each addressing a specific stage of the assessment, from product stage to end of life. The N15978 framework provides a comprehensive and internationally consistent structure for building LCA, ensuring all relevant lifecycle stages are assessed and that assessments conducted in different countries are methodologically comparable. A comprehensive LCA quantifies environmental impacts across multiple impact categories, recognizing that building materials can have significant environmental burdens beyond their carbon footprint. These impacts must be considered in any sustainability assessment. Different materials show very different environmental impact profiles across categories. Materials with low GWP may have high human toxicity or freshwater consumption impacts, reinforcing the importance of comprehensive LCA over single metric assessments in material specification decisions. The quality and reliability of LCA results depend fundamentally on the quality of the underlying data. Understanding the different types of LCA data available, their relative quality, and their appropriate application context is essential for practitioners conducting or commissioning building embodied carbon assessments. The difference between facility-specific EPD data and generic database values can be 30 to 50% for the same material category, making data source one of the most important determinants of assessment accuracy and demonstrating the significant value of manufacturer EPD programs in improving LCA quality. Allocation is the procedure for assigning environmental impacts between multiple products or functions of a single production system. ISO 14044 establishes a hierarchy preferring physical causality-based allocation, mass-based allocation, and economic allocation, with system expansion as the preferred approach where possible. The treatment of biogenic carbon, the carbon stored in biological materials like timber, is one of the most technically nuanced and professionally important aspects of bio-based material assessment. Practitioners must understand both the potential climate benefits and the conditions under which those benefits are valid. The annual carbon benefit of timber over concrete depends significantly on end-of-life fate, with energy recovery at end of life spurring optimal benefit through fossil fuel displacement. The comparison with concrete shows a substantial carbon benefit from timber even when biogenic carbon is fully released at end of life. A critical dimension of professional LCA practice is the assessment and communication of uncertainty. Sensitivity analysis and Monte Carlo simulation are essential tools for understanding how variability in input parameters affects LCA results, ensuring they are used appropriately in decision-making. The practical application of LCA methodology is supported by a growing ecosystem of software tools. These range from comprehensive standalone LCA platforms to integrated design plugins, simplifying carbon analysis and supporting decision-making in building design. Tool selection should be matched to use case. EC3 is optimal for procurement stage decisions, one-click LCA for full building assessment, and SEMA Pro or Open LCA for EPD development and research. BIM integration significantly reduces data entry time and enhances the quality of results. The Brock Commons Tallwood House is an example of how LCA can be applied to achieve significant carbon reductions in building projects. This landmark study demonstrated the potential of mass timber construction to achieve near carbon-neutral structures through careful material selection and lifecycle assessment. The structural substitution of mass timber for concrete represents the primary source of embodied carbon reduction. The comparison of carbon savings in Brock Commons highlights how mass timber building achieves a near-zero net carbon balance. Life cycle assessment is the scientific foundation of credible building materials sustainability practice. Mastering its methodology, understanding data requirements, interpreting results with nuance, and communicating with precision are the keys to transforming sustainability goals into actionable strategies. Embodied carbon is a critical metric for building professionals, focusing on its quantification, reduction, and reporting. It's the most urgent and consequential challenge in the construction industry today. Embodied carbon must be understood across its life cycle: upfront, recurrent, and whole life. Each phase impacts the environment differently, requiring precise definitions for effective management. The scope of embodied carbon reporting significantly affects the carbon figures. Professionals must carefully define boundaries to ensure accurate comparisons and reporting. Accurate calculation of embodied carbon requires a systematic approach, using defined methodologies to ensure credibility and comparability across projects. Embodied carbon assessment accuracy changes throughout project stages, highlighting the importance of early engagement and precise estimations. Embodied carbon benchmarks provide reference values for performance evaluation, helping professionals compare against typical and advanced projects. There's a notable difference in embodied carbon between best practice and typical buildings, emphasizing the need for targeted strategies in the UK market. Hotspot analysis helps identify where embodied carbon originates, focusing on areas like structure, envelope, and MEP services for targeted reductions. In office buildings, the structure and upper floors are major contributors to embodied carbon, guiding teams to focus on these areas for reduction. 7 key strategies can significantly reduce embodied carbon, from design optimization to low-carbon product specification, offering a comprehensive approach. Combining strategies like structural optimization and recycled content can achieve up to a 48% reduction in embodied carbon, showcasing the power of integrated approaches. Concrete offers the largest opportunity for carbon reduction in construction, with strategies like SCM substitution providing significant benefits. Substituting cement with SCMs can drastically reduce embodied carbon, aligning with science-based targets for sustainable construction. Embodied carbon reporting frameworks ensure consistent data application, supporting regulatory compliance and enhancing credibility across the industry. Professionals must navigate various reporting frameworks, ensuring assessments meet all necessary requirements for comprehensive compliance. Science-based targets guide the reduction of embodied carbon, aligning with global climate goals and promoting sustainable building practices. The Maggie's Center case study illustrates innovative approaches to reducing embodied carbon, showcasing successful strategies in real-world applications. Embodied carbon is a critical focus for the built environment's net zero transition, emphasizing the importance of rigorous quantification, reduction, and transparent reporting. Concrete is the most used material on Earth, and its production is a major contributor to carbon emissions. Innovations in sustainable concrete and cement are crucial for reducing this impact. The scale of the challenge is immense, but the imperative to act is clear. Transforming how cement is manufactured, specified, and used is essential for a sustainable future. Cement production emits CO2 through 2 main processes: calcination and combustion. Calcination accounts for 60% of emissions, while combustion of kiln fuel contributes 35%. Addressing these emissions requires a focus on both process efficiency and alternative energy sources. Portland cement production is a significant source of CO2 emissions, with 4.1 billion tons produced annually. Understanding the sources of these emissions is key to developing strategies for reduction. The clinker-to-cement ratio is a critical factor in reducing cement's carbon footprint. By increasing the use of supplementary cementitious materials, the industry can significantly lower emissions and move towards net zero targets. Improving the clinker-to-cement ratio by just 0.01 per year can significantly impact emissions. This requires a shift towards using more supplementary materials and innovative production techniques. Supplementary cementitious materials like GGBS, fly ash, and silica fume are essential for reducing the carbon footprint of cement. These materials offer a sustainable alternative to traditional Portland cement. Comparing the properties of different supplementary cementitious materials helps in making informed decisions for sustainable construction. Each material offers unique benefits in terms of carbon reduction and performance. Limestone calcined clay cement, LC3, is a groundbreaking innovation in low-carbon cement chemistry. It offers significant carbon reduction by using abundant, globally available raw materials. LC3 cement has the potential to significantly reduce global CO2 emissions. Its adoption can lead to substantial environmental benefits and support global sustainability goals. Alternative binder systems like geopolymer cement and calcium sulfoaluminate cement offer promising pathways for deep decarbonization. These innovations are crucial for reducing the carbon footprint of cement production. Novel cement binder systems are emerging as viable options for reducing carbon emissions. These systems offer significant potential for sustainable construction and decarbonization. Carbon capture and storage is essential for eliminating process emissions in cement production. Technologies like post-combustion capture and oxyfuel combustion are paving the way for a sustainable future. Decarbonization pathways for cement involve a combination of technologies to achieve net zero by 2050. Clinker substitution and carbon capture are central to these efforts. Recycled aggregate concrete supports the circular economy by recovering material value from demolition waste. This approach reduces environmental impact and promotes sustainability in construction. Low-carbon concrete specifications focus on reducing embodied carbon through innovative mix designs. These specifications are crucial for sustainable construction practices. Specifying low-carbon concrete involves translating technical knowledge into construction practices. This includes performance-based specifications and contractual carbon obligations. Designing for disassembly and reuse supports the circular economy in construction. This approach maximizes material recovery and extends the life cycle of concrete structures. Holcim's Eco-Packed cement demonstrates the potential for industrial-scale deployment of low-carbon solutions. This practical example highlights the importance of innovation in sustainable construction. Concrete's decarbonization begins with the specification decisions made today. By mastering the science and navigating the emerging landscape, professionals can drive meaningful change in the industry. Steel and aluminum are the backbone of modern construction, offering strength and versatility. This chapter explores advanced techniques for reducing carbon emissions while maintaining structural integrity. Discover how these metals can be both sustainable and high-performing. The carbon footprint of steel is largely determined by its production method. The blast furnace route is carbon-intensive, while the electric arc furnace offers a greener alternative by using recycled steel and renewable energy. Understanding these differences is crucial for sustainable engineering. This chart illustrates the CO2 emissions across various steel production methods. Transitioning to electric arc furnaces powered by renewable energy can significantly reduce carbon intensity, paving the way for a more sustainable future in steel manufacturing. Green steel production leverages hydrogen as a cleaner alternative to coal, drastically cutting emissions. By using renewable electricity, this method promises near-zero carbon steel, setting a new standard for environmental responsibility in the industry. Transitioning from traditional steel production to hydrogen-based methods can drastically cut carbon emissions. This pathway highlights the potential for significant environmental benefits, showcasing a future where steel production aligns with climate goals. Steel is the most recycled material globally, with high recycling rates reducing the need for new production. This slide explores how recycling contributes to energy savings and supports a circular economy, emphasizing the importance of sustainable practices. This graph compares the carbon footprint of recycled versus primary steel. By maximizing recycling, we can significantly lower embodied carbon, highlighting the importance of sustainable end-of-life strategies for structural metals. Aluminium is crucial in construction but comes with a high carbon cost. By focusing on recycled aluminium and renewable energy, we can reduce its environmental impact, making it a more sustainable choice for modern building projects. The carbon intensity of aluminium production is heavily influenced by the electricity source. This comparison underscores the importance of renewable energy in reducing the carbon footprint of aluminium, promoting a cleaner production process. Sustainable metal production is supported by rigorous standards and certifications. These frameworks ensure environmental performance and help industries meet global sustainability goals, fostering responsible sourcing and production practices. Certification coverage for steel and aluminium is expanding, reflecting a growing commitment to sustainability. These certifications ensure that production processes meet high environmental standards, driving the industry towards greener practices. Reducing embodied carbon in construction involves using materials more efficiently. Structural optimization techniques can significantly cut material use while maintaining performance, offering a practical approach to sustainable building design. This comparison highlights the impact of structural optimization on embodied carbon in office buildings. By selecting efficient materials and designs, we can achieve substantial carbon reductions, aligning construction practices with sustainability goals. Specifying sustainable metals involves integrating carbon reduction into engineering and design. By adhering to strict specifications and certifications, we can ensure that construction projects meet environmental standards and contribute to a sustainable future. The Eden project exemplifies how aluminium's carbon intensity has decreased over time. By adopting modern specifications, significant carbon reductions have been achieved, showcasing the potential for sustainable innovation in construction. Steel and aluminium are at the forefront of decarbonization efforts. Through recycling, green hydrogen, renewable electricity, and responsible standards, these materials are transforming the construction industry, paving the way for a sustainable future. Timber and bio-based materials offer a sustainable path to reducing carbon emissions in construction. These materials not only store carbon but also provide structural and aesthetic benefits, making them a compelling choice for modern building projects. The sustainability of timber is closely linked to forest management. By understanding carbon pools and the factors affecting net climate benefits, we can optimize timber use for environmental sustainability. Efficiently managed forests ensure that carbon storage is maximized, with timber products offering significant carbon preservation and long service life, contributing to a sustainable building cycle. Certification programs like FSC and PEFC ensure responsible sourcing of timber, promoting ecological integrity and biodiversity while supporting sustainable construction practices globally. Global certification coverage is expanding, ensuring that more forests are managed sustainably. This growth supports the increasing demand for certified timber in construction. Mass timber engineering has revolutionized construction, offering innovative solutions like CLT and glulam that enhance structural integrity and sustainability in modern buildings. Engineered wood products like CLT and glulam offer superior structural and environmental performance, making them ideal for sustainable construction projects. Tall timber buildings showcase the potential of mass timber construction, achieving significant carbon reductions and setting new standards for sustainable architecture. The global growth of tall timber buildings highlights their role in reducing carbon emissions, with innovative designs pushing the boundaries of sustainable construction. Bio-based materials like hempcrete and straw bale expand the palette of low-carbon building options, offering sustainable alternatives to conventional materials. Bio-based materials consistently outperform conventional alternatives in carbon performance, making them a key component of sustainable building strategies. Timber in interior design offers biophilic benefits and carbon storage, enhancing the sustainability and aesthetic appeal of building interiors. Fire safety in timber buildings is ensured through advanced design techniques, providing robust protection and supporting the growth of timber construction globally. Durability and moisture management are crucial for timber and bio-based materials, ensuring long-term performance and sustainability in construction. The Stathouse Murray Grove project exemplifies the potential of mass timber construction, demonstrating significant carbon savings and inspiring future sustainable building projects. The mass timber market is projected to grow significantly, offering substantial carbon savings and reshaping the future of sustainable construction. Building with living carbon emphasizes the importance of sustainable materials in construction, highlighting the role of timber and bio-based materials in achieving environmental goals. In this chapter, we delve into the world of insulation, glass, and building envelope materials. These components are crucial for maintaining comfort in buildings while managing carbon costs. We'll cover topics like insulation, glazing, cladding, and roofing, highlighting their roles in energy efficiency and sustainability. Insulation materials are paradoxical. They save energy but have high carbon footprints. The carbon payback period varies, with significant savings in colder climates. As energy grids decarbonize, the focus shifts to reducing carbon in insulation materials themselves. Whole-life carbon payback analysis shows how different insulation types impact carbon savings over a building's lifetime. Immediate benefits can be seen with certain bio-based materials, emphasizing the importance of considering both embodied and operational carbon. Insulation materials like mineral wool, EPS, and PIR have distinct environmental profiles. Each has varying levels of embodied carbon and thermal performance, influencing their suitability for different applications. A scatter plot reveals the relationship between thermal conductivity and embodied carbon in insulation materials. This comparison helps identify products that offer the best balance of performance and sustainability. Bio-based insulation materials, such as hemp and cork, offer carbon-negative benefits and improved environmental performance. These materials are increasingly popular for their sustainability and compatibility with modern building standards. A comparison of bio-based versus conventional insulation highlights the environmental advantages of bio-based options. Despite some trade-offs, bio-based materials often provide better overall sustainability. Glazing systems play a significant role in building carbon footprints. Innovations like low-emissivity coatings and electrochromic glazing enhance thermal performance while reducing embodied carbon. A bubble chart illustrates the trade-off between performance and embodied carbon in glazing systems. Optimal specifications balance these factors to achieve energy efficiency and sustainability. Wall cladding materials vary in their carbon footprints and durability. Options like brick, fiber cement, and timber offer different benefits, influencing their selection based on environmental and performance criteria. An analysis of cladding materials shows the relationship between embodied carbon and service life. This helps in selecting materials that offer long-term sustainability and performance. Roofing systems, including green and cool roofs, significantly impact a building's carbon footprint. Understanding their embodied carbon and benefits is crucial for sustainable building design. A comparison of roofing systems highlights their sustainability performance. Factors like embodied carbon and operational savings are key in determining the best options for eco-friendly construction. Airtightness and vapor control are essential for reducing operational carbon in buildings. Innovations in low-carbon membrane systems enhance these aspects, contributing to overall building efficiency. The Bullitt Center in Seattle exemplifies sustainable building practices. With features like triple-glazed windows and FSC-certified cladding, it demonstrates the integration of energy efficiency and low-carbon materials. The key takeaway is the importance of considering both operational and embodied carbon in building materials. By focusing on insulation, glazing, and whole-life thinking, we can make informed decisions for sustainable construction. The linear model of building materials production is unsustainable, with significant environmental impacts. This chapter explores how circular economy principles can transform the industry, focusing on recycled, reclaimed, and circular materials. The circular economy framework is built on 3 principles: designing out waste, keeping products in use, and regenerating natural systems. These principles are crucial for sustainable building practices. The hierarchy of value retention in building materials emphasizes maintaining, reusing, and remanufacturing to preserve value and reduce carbon consumption, minimizing landfill use. Recycled content in mainstream building materials is crucial for sustainability. Various materials like steel, glass, and concrete incorporate significant recycled content, reducing environmental impact. There's a gap between current and potential recycled content in building materials. Bridging this gap can significantly reduce primary material consumption and enhance sustainability. Reusing structural steel and timber components offers high value in the circular economy, reducing carbon emissions and overcoming barriers to sustainable construction practices. Reusing structural steel significantly reduces carbon emissions compared to primary steel production. The market for reused steel is growing, driven by regulatory and economic incentives. Gypsum plasterboard recycling is a prime example of closed-loop recycling in construction, offering technical feasibility, carbon benefits, and strong UK infrastructure support. The UK gypsum plasterboard circular economy shows significant recycling rates and carbon savings, highlighting the potential for closed-loop systems in construction materials. Ceramic, stone, and masonry materials offer durability and aesthetic value, with opportunities for recovery and reuse, contributing to a sustainable circular economy. Comparing embodied carbon in primary versus reclaimed materials reveals significant savings, emphasizing the environmental benefits of using reclaimed building materials. Designing for disassembly enables efficient recovery of materials at the end of a building's life, supporting circular economy principles and extending material life cycles. Different connection types in building design affect material recovery rates, with reversible connections offering higher recovery potential, supporting sustainable construction. Digital material passports provide essential data for circular construction, enhancing transparency and enabling efficient material recovery and reuse throughout a building's lifecycle. Digital material passports facilitate data flows across the building lifecycle, improving recovery rates and creating financial value, essential for sustainable construction practices. Rotor deconstruction exemplifies a successful circular materials platform, recovering and reusing building components, and demonstrating the economic viability of circular practices. The circular economy in building materials is achievable through material specification, design for disassembly, and digital material passports, paving the way for sustainable construction. Understanding the materials that make up our buildings is crucial for health and safety. This chapter explores the impact of building materials on indoor environmental quality, focusing on how they affect the health of occupants and construction workers. Indoor air quality is a significant public health issue, with higher VOC concentrations and premature deaths linked to poor air quality. The economic cost of poor indoor air quality is substantial, highlighting the need for better building practices. Building materials are a major source of indoor chemical pollutants. Understanding the subcategories and key pollutants helps designers make informed choices to improve indoor air quality. Volatile organic compounds, VOCs, are harmful chemicals found indoors. Formaldehyde, a known carcinogen, is a significant concern. Regulatory thresholds guide safe levels to protect health. VOC emission rates vary significantly across materials, emphasizing the importance of material selection in construction. Regulatory limits help manage these emissions to ensure safety. Identifying chemicals of concern is vital for safe building environments. The Living Building Challenge Red List and other frameworks guide the exclusion of harmful substances. The LBC Red List categorizes chemicals by risk in building materials, emphasizing the need for systematic health assessments over simple category assumptions. Material health certifications like HPD, Declare, and Cradle to Cradle provide rigorous standards for healthier building materials, ensuring transparency and safety. Comparing material health certification programs reveals varying scopes and requirements, helping stakeholders choose the best fit for their projects. PFAS, known as forever chemicals, pose significant health risks due to their persistence and bioaccumulation. Avoidance is key to achieving material health excellence. Regulatory timelines for PFAS are evolving, with increasing restrictions aimed at reducing exposure and risk in building materials. The WELL Building Standard focuses on enhancing health and well-being through improved air, materials, and transparency in construction practices. WELL certification is growing rapidly, emphasizing materials requirements and market growth, with a focus on sustainable and healthy building practices. Protecting workers during construction is crucial. Identifying and managing exposure to harmful chemicals like silica dust and isocyanates ensures safety. The Bullitt Center exemplifies successful material health practices, demonstrating the impact of comprehensive chemical management on market transformation. Material health is essential for sustainability, requiring transparency, certification knowledge, and a commitment to protecting all people involved in building processes. Green building rating systems are essential frameworks that guide sustainable material specification in the construction industry. They help clients, investors, and regulators evaluate environmental credentials and translate sustainability performance into actionable decisions. LEED is a globally recognized green building certification program that focuses on energy and environmental design. It includes key credit categories like location, water efficiency, and materials, emphasizing life cycle impact reduction and responsible sourcing. LEED version 4.1 allocates points based on materials and resources, with a total of 110 points available. It emphasizes EPD achievement and LCA adoption, encouraging sustainable building practices. BREEAM is a leading environmental assessment method that evaluates buildings on various criteria, including management, energy, and pollution. It highlights responsible sourcing and life cycle assessment as key credits. BREEAM certification focuses on materials credit contribution, with a target of 65% for new commercial buildings. It emphasizes responsible sourcing and durability, aiming for excellence in sustainability. The Living Building Challenge sets the highest standards for green building, focusing on net positive carbon impact and sustainable materials. It promotes ecological stewardship and community equity. A comparison of green building rating systems reveals varying material requirements, with each system prioritizing different sustainability aspects like carbon, health, and transparency. DGNB, the German Sustainable Building Standard, emphasizes environmental and economic quality. It integrates life cycle assessment and circular economy principles to enhance sustainability. DGNB certification evaluates environmental quality criteria and LCA requirements, offering different levels of certification like bronze, silver, and gold based on performance. Green Star and other national rating systems in Asia-Pacific focus on reducing embodied carbon and enhancing sustainability. They adapt to regional needs, offering tailored certification processes. The global green building certification market is expanding, with a significant increase in certified space and annual growth. This trend highlights the growing importance of sustainable building practices worldwide. Integrating multiple rating systems like LEED, BREEAM, and WELL can streamline certification processes and enhance sustainability outcomes. Unified tools help reduce the certification burden. LEED and BREEAM credit alignment focuses on shared materials and resources, promoting dual certification efficiency. This overlap encourages evidence reuse and streamlined processes. The evolution of rating systems is moving towards mandatory carbon limits, with milestones like LEED for net zero and BREEAM whole life carbon. These changes reflect a commitment to reducing embodied carbon in buildings. The timeline of embodied carbon in rating systems shows a shift from no recognition to mandatory limits, highlighting the increasing focus on carbon reduction in sustainable building practices. Bloomberg's European headquarters exemplifies BREEAM outstanding certification, showcasing innovative design and sustainability achievements like reduced material quantities and improved thermal performance. Green building rating systems are vital for defining material requirements and ensuring sustainable practices. They serve as technical frameworks, market intelligence tools, and professional standards for the industry. In an era of escalating regulatory requirements and public accountability, the sustainability of building materials is under scrutiny. Every sustainability statement must be independently verified, ensuring transparency and trust in the industry. Environmental Product Declarations, or EPDs, are standardized documents that quantify the environmental impacts of a product. They are governed by specific standards and include mandatory impact categories to ensure comprehensive assessment. The N15804A2 EPD structure provides a detailed framework for assessing environmental impacts, capturing cradle-to-grave data and other essential environmental concerns. EPDs are proliferating globally, with numerous programs ensuring that verified EPDs are accessible to professionals and stakeholders, reflecting a growing demand for transparency and sustainability. The rapid growth of EPD registrations from 2010 to 2024 highlights the increasing adoption of EPDs, driven by regulatory demands and market needs for sustainable practices. Critically evaluating EPDs involves assessing their quality, credibility, and comparability. This process helps identify any red flags that could undermine the reliability of sustainability claims. The EPD Quality Assessment Framework provides criteria for evaluating EPDs, ensuring they meet industry standards and offer reliable data for decision-making. Material health declarations reveal the chemical composition of building products, supporting transparency and safety in the supply chain for sustainable practices. The HPD database has expanded significantly, with certain categories showing strong market coverage, emphasizing the importance of transparency in material health. Responsible sourcing certification ensures that building materials are ethically sourced and manufactured, adhering to environmental, social, and governance standards. Various tools enhance supply chain transparency, covering aspects like EPDs, HPDs, and responsible sourcing, ensuring comprehensive sustainability practices. The EC3 tool, launched in 2019, helps in assessing and reducing the embodied carbon in construction materials, promoting a focused approach to sustainability. The EC3 tool demonstrates significant carbon savings in construction, showcasing its effectiveness in promoting sustainable practices through precise data analysis. Digital platforms are revolutionizing supply chain transparency, enabling access to essential data and tools for assessing and improving sustainability in construction. An integrated supply chain workflow combines digital tools and data to streamline processes, enhancing efficiency and sustainability in procurement and construction. Saint-Gobain's EPD program exemplifies industry leadership in sustainability, demonstrating strategic investment in transparency and quality assurance. The foundation of genuine sustainability practice lies in verified, comparable, and accessible data, ensuring credible and environmentally responsible outcomes. The transition of embodied carbon from a voluntary sustainability aspiration to a legally enforceable regulatory obligation is one of the most significant and rapidly accelerating transformations in the history of built environment governance. This CDG training chapter develops comprehensive knowledge of the global regulatory landscape, from the most advanced national frameworks in France and the Netherlands through emerging mandatory requirements in the UK, EU, US, and major Asia-Pacific markets. France's RE2020 regulation sets a new benchmark for residential buildings, establishing a maximum carbon score threshold for life cycle greenhouse gas emissions. This standard is not only the most advanced but also represents a significant market shift, with over 30% of the market growth in the timber sector since its implementation. France RE 2020 introduces progressive tightening of carbon score thresholds, encouraging structural system reductions and innovative construction applications. This has led to a 34% growth in mass timber and an 18% reduction in embodied carbon. The Netherlands has been a pioneer in mandatory building lifecycle assessments, setting a precedent for other countries. The MPG works by calculating scores using the Dutch National LCA database, ensuring a comprehensive environmental performance comparison. The Dutch market has responded dynamically to MPG requirements, with a steady decrease in building scores and increased market participation. This evolution highlights the effectiveness of mandatory LCA in driving sustainable construction practices. The UK is leading the way in mandatory whole-life carbon assessment, integrating it into planning policy requirements. This approach is progressively influencing the market, with Scotland and England setting the pace for regulatory adoption. The UK's regulatory trajectory is moving towards mandatory whole-life carbon assessment in building regulations. This timeline outlines the gradual adoption and anticipated outcomes, including a 45% increase in London WLC assessments. The European Union is developing a comprehensive regulatory framework for building materials sustainability. This includes the revised Construction Products Regulation and the Levels Voluntary Framework, aiming for a harmonized approach across member states. The CPR mandatory EPD requirements will drive transparency across the European construction market, with 90% of construction product value expected to be covered by mandatory EPD requirements by 2030. The United States has taken a federal procurement-led approach to embodied carbon regulation, using the purchasing power of the federal government as a market signal. This initiative is transforming the market by encouraging sustainable practices in federally funded projects. U.S. Buy Clean thresholds are set to ensure the majority of products comply with carbon intensity standards, promoting sustainable procurement and market transformation. Carbon pricing is a critical tool in reducing greenhouse gas emissions, affecting the competitiveness of high-carbon versus low-carbon materials. The EU emissions trading system and the Carbon Border Adjustment Mechanism are key components in this strategy. An examination of EU ETS carbon prices reveals significant impacts on production costs for major building materials, creating a commercial imperative for adopting low-carbon alternatives. Infrastructure construction is a major contributor to global carbon emissions. Key regulatory developments, such as PA 2080, are crucial in managing carbon in infrastructure projects, ensuring sustainable growth. A maturity assessment of the global embodied carbon regulatory landscape shows varying levels of advancement, with countries like France and the Netherlands leading the way in regulatory maturity. Amsterdam's policy on circular buildings has sparked significant innovation in the Dutch construction market, demonstrating the power of progressive municipal procurement policies in driving sustainability. Embodied carbon regulation is no longer a future possibility, it's a present reality in many regions. Mastering this regulatory landscape is crucial for advancing sustainability in construction globally. Sustainable materials specification and procurement is crucial for translating sustainability intentions into actionable construction obligations. This involves ensuring that sustainability commitments are clearly defined, measurable, and effectively implemented in construction projects. The specification hierarchy guides sustainable materials from high-level policy to detailed technical specifications. Each level, from client policies to verification, ensures alignment with sustainability goals, addressing common specification failures. A visual representation of the sustainable materials specification hierarchy shows the progression from broad policies to specific technical requirements, ensuring alignment with sustainability objectives at every level. Writing effective embodied carbon specifications involves balancing performance-based and prescriptive approaches. This ensures that carbon performance is accurately measured and verified, supporting sustainable construction practices. Setting embodied carbon performance thresholds involves a multi-step process, from budgeting to supply chain checks. This ensures that specifications are both ambitious and achievable, addressing common failures in carbon management. Responsible sourcing specifications for timber, steel, and concrete require tailored approaches. These ensure compliance with sustainability standards and address the unique challenges of each material category. The requirements matrix outlines the certification, evidence, and compliance needs for different materials. This helps ensure that sourcing specifications meet sustainability standards across various material categories. Integrating sustainability criteria into pre-qualification and tender evaluation processes enhances sustainable procurement. This approach moves sustainability assessment upstream, influencing supplier selection and contract awards. The Tender Sustainability Evaluation Framework allocates a specific weight to sustainability criteria, ensuring that environmental performance is a key consideration in contractor selection and project execution. Implementing site-based sustainability monitoring ensures that evidence collection is integrated into the construction process. This proactive approach prevents last-minute certification issues and supports continuous improvement. The 6 quality gates in sustainability evidence management provide structured checkpoints throughout the construction process. This prevents common failures and ensures compliance with sustainability standards. Outcomes-based contracting focuses on achieving specific carbon reduction targets. This innovative approach aligns contractor incentives with sustainability goals, driving commercial accountability and environmental performance. The incentive structure for outcomes-based carbon contracts demonstrates how exceeding carbon reduction targets can be a commercial opportunity, encouraging contractors to innovate and excel in sustainability. Effective sustainable procurement involves engaging the supply chain and building capacity through assessments, workshops, and reduction strategies. This ensures that sustainability is achievable and maintained across projects. The Sustainable Procurement Maturity Model outlines the progression from reactive to transforming practices. This model helps organizations optimize carbon performance and achieve higher sustainability standards. Lend-Lease's Sustainable Procurement Program exemplifies how sustainability can be integrated into construction projects. Their commitment to zero carbon and innovative practices demonstrates the commercial viability of sustainable procurement. The key takeaway emphasizes the importance of sustainable materials specification and procurement in bridging the gap between sustainability and construction. It highlights the role of professionals in ensuring that buildings are both sustainable and commercially viable. Welcome to Chapter 14, where we delve into the complete carbon picture of buildings. We explore how integrating embodied carbon reduction, operational energy optimization, and residual carbon management forms a unified net zero strategy. Whole life carbon assessment quantifies greenhouse gas emissions across a building's life cycle. It includes upfront, construction, in-use, operational, end-of-life carbon, and beyond boundary benefits, providing a comprehensive view of a building's carbon footprint. This graph illustrates the cumulative carbon accumulation over a building's life cycle. It compares fixed and decarbonizing grid scenarios, highlighting the impact of operational and embodied carbon on overall emissions. Operational carbon refers to emissions from energy use in buildings. It includes regulated and unregulated energy, with a focus on reducing the performance gap between design and actual energy consumption. This chart shows how grid decarbonization affects the balance between embodied and operational carbon. It highlights the transition towards renewable electricity and the impact on carbon emissions. The performance gap is the difference between theoretical and actual energy performance. Addressing this gap involves rigorous analysis and communication to ensure buildings meet their energy efficiency goals. This analysis reveals the disparity between design and measured energy use in UK non-domestic buildings. It emphasizes the need for accurate predictions and adjustments to close the performance gap. Passive design strategies focus on reducing energy demand through building form and natural ventilation. These strategies are crucial for minimizing both embodied and operational carbon, enhancing energy efficiency. This graph demonstrates the potential of passive design strategies to reduce energy demand significantly. It shows the cumulative impact of various measures, emphasizing their role in achieving energy efficiency. To complement passive design, renewable energy systems are essential. On-site and off-site strategies, like integrated PV and heat pumps, help achieve net zero carbon by supplying renewable energy. This analysis outlines the sources and reductions of carbon in a net zero building. It highlights the importance of design and net zero balancing in achieving significant carbon reductions over a building's lifecycle. High-quality carbon offsetting and removal technologies are vital for managing residual emissions. They ensure that buildings meet net zero claims by balancing any remaining carbon footprint. This assessment evaluates the quality of carbon offsets based on various criteria. It ensures compliance with net zero building standards, focusing on permanence, measurability, and co-benefits. Investing in whole-life carbon reduction offers financial benefits, including rental premiums and reduced risks. This slide highlights the economic incentives for sustainable building practices. This analysis shows the financial return on carbon investment for commercial offices. It demonstrates enhanced returns and reduced payback periods, making a strong case for sustainable investments. The Crystal in London exemplifies successful integration of net zero strategies. It showcases design objectives, renewable energy use, and post-occupancy verification, setting a benchmark for sustainable buildings. The key takeaway is the importance of a unified carbon strategy. By integrating embodied carbon reduction, operational energy optimization, and residual carbon management, buildings can achieve true sustainability. You've completed a rigorous program in building materials sustainability, equipping you with the skills to lead in this critical field. This course positions you to influence standards, evolve technologies, and tighten regulations. The demand for building materials sustainability professionals is surging globally, driven by regulatory and market forces. This expertise is crucial for navigating the evolving landscape of sustainable construction. Building materials sustainability roles are among the fastest growing and best paid in the construction sector. Job postings and salaries are increasing significantly, reflecting the high demand for these skills. Career pathways in building materials sustainability are diverse, spanning consultancy, property development, construction, manufacturing, and policy. Each path offers unique opportunities for impact and advancement. The career development pathway for sustainability professionals includes foundational, developmental, and leadership stages, each offering opportunities for growth and specialization. Key competencies for career advancement include technical proficiency, regulatory literacy, and communication skills. These are essential for leading in the field of building materials sustainability. The competency framework outlines the required levels at each career stage, ensuring professionals meet industry standards and advance effectively in their careers. Professional certifications and credentials are vital for career advancement, providing recognition and validation of expertise in building materials sustainability. The certification landscape offers various options, each with specific values and requirements, to enhance your professional standing in sustainability. Building your professional profile involves publishing content, presenting at conferences, and participating in professional bodies, all of which enhance your visibility and network. A professional visibility strategy balances career impact with time investment, guiding you to maximize your influence in the field efficiently. The future of building materials sustainability is shaped by AI, digital product passports, and green hydrogen, among other innovations, driving the industry forward. Emerging professional frontiers from 2024 to 2035 include new standards and technologies, offering exciting opportunities for growth and innovation in sustainability. Apply your expertise immediately by integrating technical knowledge into your current projects, enhancing your impact and advancing your career. CDG Training offers a comprehensive online certification journey, allowing you to learn at your own pace and gain recognized credentials in building materials sustainability. A fully automated online learning journey provides flexibility and accessibility, ensuring you can achieve certification without compromising your professional responsibilities. Certification transforms careers, as illustrated by a professional's journey from technical specialist to leadership, showcasing the impact of advanced training. Your certification is a foundation for impactful contributions to sustainability, guiding every project and regulation you influence. Enrolling in CDG Training is your next big step, offering growth, recognition, and the opportunity to significantly reduce carbon emissions in your projects. Thank you for choosing CDG Training, your partner in achieving excellence in building materials sustainability and making a lasting impact on the global built environment.